We can wrap up our entire semester, and this chapter specifically, by talking about antimicrobial resistance. When we say antimicrobial resistance, we mean the ability to grow even though they're being treated with antibiotics, and this is what we call an acquired ability. So the microorganism evolved this ability that it never had before. There are some reasons that organisms can naturally be resistant to certain antibiotics. That could be that the organism is impermeable to the antibiotic, so the antibiotic can't get in to that particular organism. The organism can inactivate the antibiotic. The organism might modify the target of the antibiotic. The organism may have a resistant biochemical pathway. The organism may be able to pump out the antibiotics. So, for example, there's a type of antibiotic called bacitracin. You might have heard of bacitracin because you can often get it over the counter in ointments. Bacitracin is produced by Bacillus bacterium. So why does it not kill Bacillus? Well, because they can pump it out. So there are some organisms that are just naturally resistant to certain types of antibiotics, and for that, we're not super concerned. We just would not use that antibiotic to treat that organism. What we're concerned about are organisms that used to be sensitive to an antibiotic but no longer are, because then that tells us that they have acquired antimicrobial resistance. So how do they acquire antimicrobial resistance? Well, they can pick up one of those 5 features we talked about that are shown here on this slide and have a new function or a new feature that they never had before. Antibiotic resistance is not a new thing, and the sharing of antibiotic resistance is not a new thing. It has just become more prevalent and more prominent because as humans, we try to use these compounds to treat our infections. And when they develop resistance and we can no longer treat our infections, we are aware of this fact and we find it very concerning. Whenever a microorganism is exposed to an antimicrobial compound, whether we're talking about, a patient who's been prescribed an antibiotic that's been given to chickens in an agricultural facility, or simply an antibiotic produced by a soil bacterium to fight off other soil bacteria, that can select for resistant organisms. Those organisms in the soil, they don't want to be killed, so if they can evolve resistance to the antibiotic produced by another bacterium, they will. Microbes growing in a chicken don't want to be killed, so if they can evolve resistance, they will. And of course, microbes growing in us don't want to be killed, so if they can evolve resistance, they will. The overuse of antibiotics or the inappropriate use of antibiotics is what drives the significant increases we see in resistance worldwide. I like this table because it shows you the antimicrobial compound, the year it was released, which organism was first identified to be resistant, and in which year. So penicillin, released in 1943, penicillin-resistant strep pneumoniae in 1967. Penicillinase producing Neisseria gonorrhea, so basically penicillin-resistant gonorrhea, 1976. Okay, vancomycin, 1958, 1988, that's a good amount of time. Amphotericin B, which is an antifungal, 1959. Amphotericin B resistant Candida, 2016, okay. Methicillin, 1960. Methicillin-resistant Staph aureus, 1960. Oh, that's a little bit more concerning. Some of these extended spectrum cephalosporins or extended spectrum beta-lactams in 1980, extended spectrum beta-lactamases, 1983. Distance. This one's my favorite though. Fluconazole was FDA approved in 1990. We had fluconazole-resistant Candida in 1988. So by the time we were already prescribing fluconazole, we had resistance for a couple of years. And then this is a drug combination in 2015, a resistant population of Klebsiella pneumoniae the same year. And this one also produces KPC, which is a carbapenemase. So this is pretty much what you would consider to be almost a pan-resistant strain of Klebsiella. Here's daptomycin, 2003, daptomycin-resistant, methicillin-resistant Staph aureus in 2004. So the overuse of antibiotics, the introduction of antibiotics to the market, you start to get resistance, and it can happen very, very quickly. You could probably pick out any species of bacterium that causes disease in a human, and you would find resistance to at least one antibiotic in at least one strain of that particular species. So there are always going to be some drugs that you are not going to be able to use to treat some types of infections. And we do have some pathogens that have developed resistance to all known antimicrobial agents. We call those pan-drug resistant. The example that I can think of off the top of my head was a patient in Nevada in late 2016 who had an infection with a strain of Klebsiella pneumoniae that was resistant to all 26 FDA-approved antibiotics. And that patient did die of that infection. We can try to minimize the acquisition of resistance by using antibiotics correctly, following the drug dosing schedule of your physician, only using antibiotics when prescribed, finishing your course of antibiotics, not giving antibiotics to other people, etc. Resistance could be lost if the antibiotic is not used for several years, especially if we're talking about a plasmid-based antibiotic resistance. If the bacterium don't need the plasmid anymore, it is possible that they could kick that plasmid out. This is less likely with chromosomally encoded resistance because bacteria are not going to lose a piece of their chromosome. Therefore, we really need to invest in identifying and developing new antimicrobial compounds and really going after new antimicrobial targets. So that's why, we set up the lab the way we did, where you search for bacteria producing antibiotics in the soil, because who knows? Maybe one of you or maybe somebody in another class will find an antimicrobial compound that is really, really good. Often, usually like pharmaceutical chemists can modify the structure of currently used antibiotics to make a more functional antibiotic, to make one that's resistant to destruction by the cell. So we call those semi-synthetic because they have been based on a naturally occurring compound, but they've been modified in such a way that while they still might have a motif of a naturally occurring compound, the actual structure was really derived in a lab. And then, of course, we have completely synthetic compounds that were all designed in a lab, and we have combinatorial chemistry, where companies or chemistry labs will generate tens of thousands of compounds that meet these specific rules. So there's a set of rules that govern, they're biochemical rules, they're not like real rules. A set of biochemical rules that kind of govern how antibiotics should look in terms of their biochemistry. And so scientists can generate compounds that kind of follow some of these rules to see if maybe they will be not only effective in people, but also will treat bacterial infections. So here they're showing you vancomycin. You can see that it's a heavily modified compound, but it is fairly effective. Of course, we do have vancomycin resistance, but it's less common than, for example, methicillin resistance. So vancomycin is often used as kind of a last resort drug. So it can, for example, treat methicillin-resistant infections. It can be used to treat C. diff or that Clostridium difficile. It often is not given orally. It's usually given intravenously. And again, we're talking about patients who are really, really sick when they're being prescribed vancomycin over, another compound. Computational chemists are also being able to use computers to design molecules. So they might identify a particular target in a microorganism. Here they give an example, an HIV protease. And so they can model compounds which would interfere with that protease, but should not interfere with human proteins. And then those compounds can be generated in the chemistry lab, and then they can be tested. And so this is a compound that has worked against the HIV protease and is in testing. And of course, new methods to screen natural products. That's what we're doing in the lab. That's what scientists have done to identify novel antimicrobial compounds. And then combinations of drugs with an enzyme inhibitor. So if you've ever been prescribed something called augmentin, augmentin is a combination of, I believe it's either ampicillin or amoxicillin. I think it's amoxicillin. It's a beta-lactam. And it is combined with a compound called clavonic acid. Clavonic acid inhibits beta-lactamases. So even if the infectious agent produces a beta-lactamase, that would be inhibited by the clavonic acid, which allows the amoxicillin to work. You could also combine drugs that have different mechanisms of action. You could prescribe a cell wall inhibitor and a protein synthesis inhibitor. So if resistance to one shows up, the other should still be effective. Here they're showing the HIV protease and some of the drugs that were designed in a chemistry lab to help inhibit that protease.